For more videos like this for Discrete 1, you can take a look at Sarai's studies, link is in the description box below. We're told to prove that the sum of two even integers is even, meaning if we take two even integers, let's say 2 and 4, and we sum them together, its sum, which is 6 in this case, is also supposed to be even, is it? Yes. Let's take another two even integers, how about 10 and 8? Its sum is 18, is this even? Yes. And we can take another two even integers, and its sum is supposed to be even, that's what we're trying to prove, but we don't have the time to plug in every single combination of two even integers and check if the sum is even because there's infinite number of even integers. So because it's impossible to sit here and actually figure out if for every two even integers we pick, the sum is even, we have to prove that this is true using logic. Before anything, we have to identify what the domain is that we're working in. In this case, they tell us we're working with integers, so the domain is the set of all integers, which is just z with a little extra line. If they had just said numbers instead of integers, then you would have to know the fact that the only numbers that are even or odd are integers, so then you would have to say, oh yes, we're working with integers. The next thing you want to do no matter what proof you're doing is your definitions. What does it mean for integers to be even? I already covered this in the first direct proof video that I did. It's linked in Sarai's studies. You can see a whole section where I explain how to get the formula. So you can watch that if you're interested in learning why the formula is what it is. But we say that an integer s is even if and only if, that's a double implication operator, there exists, so we use the there exists quantifier, a k where, so comma means where, k is an element of the set of all integers. So it lives in the house of integers. It is an integer, however you want to read it. Subject to, so this k is constrained by, it has to follow the following condition, and that condition is that if you take k and you multiply by 2, it should give you s, this integer that is even. In other words, we're saying that for every even integer, there's another integer that if you multiply by 2, you get your even integer. And here's some color coding for you. Anyway, the next thing to do is to decide what method you're going to try first. But before that, you always want to try and see if you can write what you're trying to prove as an if-then statement. So we want to see if we can rewrite this to say prove if something, then something. And we can say we're trying to prove if I add two even integers, then the sum is even. And the reason why I wanted to write it with an if-then statement is because now we can call this proposition P and we can call this proposition Q, and that's a perfect setup to do our proof by direct proof method. Why? Because a direct proof method says we assume P to be true, and then we use axioms, theorems we already proven, definitions, properties, known equivalences, and so on to show that Q is true. So let's get started again with a direct proof. We start by assuming that P is true, but what's P? Is I add two even integers. So what does this imply? Well, it first implies that we have two integers. So let's give those integers names. Maybe I'll call one integer x and another one y. My tip to you is to not use any of the variables that you have in your definitions so you don't get confused. And we are assuming that we are adding these two integers, x and y. So this implies that we are literally adding x and y. But what does it mean for x and y to be two even integers? Well, if we're saying that x is an even integer, let's go back to the definition. If x is an even integer, then there exists another integer, k, where if you take k and multiply by 2, it's going to give you x. So in other words, if this is true, if we're assuming that we have an even integer x, then it is true that x is equal to 2 times some other integer k. So we can replace x with 2 times some integer k, and we can do the same for y because we know that y is also an even integer. So if we go back to the definition, if we have y as an even integer, if this side of the implication is true, then we can say that the other side of the implication is true, that there exists some other integer k, that if you multiply k by 2, you get y. So it is true that y is equal to 2 times some other integer k. So we can replace y with 2 times k, but here's a problem. If this is x and this is y, we're saying that x and y are the exact same thing, that they are equal to the same integer k times 2. But x and y can be different. So we want to say that this could be a different k. So we can label this k1 and k2. So essentially, I'm going to move this over here. X plus y is equal to this, where k1 and k2 are also integers. And here we use the definition of an even integer. So now where do we go from here? Well, right now we're at P and we're trying to get to Q. We're trying to show that Q is true. What does Q say? It says that the sum is even. The sum of what? The the sum of x and y. So we're trying to show that x plus y, which is the sum, is even. So how can I show that x plus y is even? Well, at the end of the day, I know that x plus y, whatever it's going to be an integer. How do I know that? Because of the closure properties of integers, which I covered in the same video that I explained how to get the definition of an even number. But in simple words, it says if you add two integers, which we know that x and y are, because we assume them to be two integers here, we just get another integer. And we can call that integer s, whatever you want. But at the end of the day, we know that it's an integer. So what do we know about an integer that is even? So if x plus y is even, then there's going to exist some integer k, where if you take k and multiply by 2, it's going to give you x plus y. So if we want to show that q is true, that the sum x plus y is even, we're going to have to show that x plus y is equal to 2 times some integer k. In other words, we have to get what x plus y is equal to, which is this right now, to look like this, to have a 2 multiplied to some integer k. And luckily for us, we have some 2's here. So this implies that x plus y, and this is just going to be some algebra, is going to be equal to 2, so we're factoring out a 2 times the quantity of k1 plus k2. Now we have that the sum x plus y is equal to 2 times something, which is very similar to the definition of an even integer, where an even integer is equal to 2 times something, but here that something is an integer. So the question is this an integer? Because if it is, then our work is done. And the answer is yes, it is. Why? Because of the closure property of integers under addition. Just a fancy way of saying if we add two integers, we're going to get another integer. We can call it k3, we can call it r, whatever you want. I'm going to call it r. And then we just drop everything else down. And we specify what r is. R is equal to k1 plus k2. And r is also an integer. Why? Because of the closure property of integers under addition. Addition because there was addition here. Now look at what we have here. We have x plus y, which is the sum, is equal to 2 times some integer r, which is really similar to the definition of an even integer. That is equal to 2 times some integer k. And it's actually the exact same thing. We managed to get x plus y, which we know is eventually going to be an integer because of the closure property of integers under addition, to be of the form of an even integer. So because of the definition of an even integer, we can conclude that x plus y is even by the definition of an even integer, and we know that x plus y is our sum. So in other words, we managed to go from p and show that q is true. We managed to go from p and show that q is true. Then we say therefore, that's what this symbol means, and then you just copy and paste what they wanted you to prove. The sum of two even integers is even, and you are done with your proof. So you do your little box, and that's it for this video. I'll see you in the next.